this question of how microwaves launched and enabled my academic and research career. So, full disclosure, my first interaction with microwaves was in the 70s when my dad had bought a microwave oven. And I came home from school before ballet, and my mother would always say, eat before and be ready when I get home from work. So I, every day, diligently heated up my food. But one day, I happened to put a Chinese container in the microwave, and the microwave caught on fire. So of course I'm like panic crazy. I finally get it open. I get this thing that's in flames in the sink, and all I can think about is my parents are going to kill me because my dad had just bought that microwave oven. I didn't understand why it caught on fire. So for many years I always wondered, what did I do wrong? And all I know is they said, you put metal in the microwave. So now I actually know why it burned, it caught on fire. But that was my first interaction with microwaves. My second interaction was when I was working at Lawrence Livermore National Laboratory, and I actually started in power electronics, and I had a wonderful professor at Texas A&M who helped me with that, and so I said, why don't you try this? And I went, and at the time it was pulse power and high power. So capacitors were about this big around, and it would take 2 technicians to move these parts. So as I'm going to learn about my new summer job, to learn about research, I'm like a junior in college, my boss gets up on a ladder, and then everybody stands back and they put a question mark on him. So I'm looking and saying, why are they putting that question mark, was a hook, why did they put that question mark on my boss? And he said, that's a grounding hook. And I said, why does he need that? And he said, well, because we need to make sure he doesn't get electrocuted when he starts to mess with this. So of course that scares me half to death. I'm thinking my mother's gonna kill me because I'm working on dangerous things. And I really struggled with that summer because I was so excited, but I was so nervous about what I was doing. And then I had to rely on these technicians to help me. But at that time, they were not very, they weren't mean, but they weren't friendly and supportive. And it scared me because they would make jokes, you know, oh, the intern and this and that. And I always wondered, would they let me hurt myself by just goofing off? So I wasn't easy with that. But I met the chief engineer. He was the head of engineering at Livermore at the time, and he asked about my summer, and I said, you know, very politely, it was okay. You know, I wasn't going to out anybody. You know, you don't snitch, right? And I really felt like I can't do that, but I don't know what I'm going to do. And so I said, he said, what would make it great? And I said, if I could move all my parts myself. And he said, well, then you want to do microwaves. And I said, really? He said, yeah. He said, in microwave frequencies, everything gets smaller. And you can do that by yourself. So at that point, I made a decision to do microwaves. And I have not stopped since then. So
the motivation for all of us.
So what I'm going to talk to you about today is I'm going to try to share with you the things that influenced my decision to consider engineering, and then to talk about how the times really influences what we get to work on in our particular discipline, both at our training level and post that. And then I'll end with talking about some of the things we're working on right now, which are very much influenced by the things that I was working on at the start of my career. Then I'm going to transition into a topic that is just important to me because it has to do with the role of women as faculty, and in particular African-American women, and where we look, how things look in the country, and then just what are some of the things that I think we as academics and as professionals should really be thinking about as we're interfacing with students, and particularly when we identify people who are either diamonds in the rough or clear talent, what we need to do to enable them, but also hopefully share with you one person's perspective of what that journey might actually look like from their point of view. So for me, I work at the University of Minnesota. We're much smaller than Michigan's department. We're about 45 faculty, 500 graduate students or so. And I work in an area that's a combination of RF, magnetics, and optics. My group is about 5 students on average. So in the talk, I'll talk about what inspired me to do this. I'll focus on microwaves, particularly the applications in communications, and now some of the things we're looking at in nanomedicine. And then I'll talk about female and minority engineering faculty, in particular what the journey looks like, and also what I think about the future. So I was really inspired by these beautiful pictures of space. I watched all of the techie movies when I was a kid, cartoons, movies, and that, I'm from Houston, Texas, so I got to see a lot of images of from NASA at the time. So everything to the left was what I saw when I was in Texas up to about 83 going to college. And I was just so fascinated by it. I really was just curious about how did they do that? And then everything on the right just kind of shows what would eventually be developed as when I was here as a student and onward. The other thing that really inspired me were astronauts. And of course, we all knew about John Glenn. I learned that in school. But I was also really inspired by the fact that these people wanted to get into this rocket and go into outer space and have whatever they needed to have. I didn't want to be an astronaut, that I knew, but I wanted to help them do what they did. I wanted to help them communicate. I wanted to contribute in any way that I could. So the pictures on the left are the astronauts that come to mind when I was an undergraduate student, and the pictures on the right are actually people that I had the opportunity to meet when I was here at Michigan. And you know one of them in the center in his younger self, Tony England. The last thing about this picture is that when I came to Michigan, by then I had formulated that, I liked this notion of space and I wanted to participate in that. And I had a dream, at least, that I would meet 2 astronauts. I was like, I hope in my lifetime I get to meet 2 astronauts. Well, I actually got to meet 3 astronauts, Tony England, Mae Jameson, and Charlie Bolden, all here. Tony was my graduate advisor, who was also in the RAD lab and is now dean at Dearborn. And then Charlie Bolden actually invited me to see him go up on an actual launch. So that last picture is a launch I actually visualized in person in Florida, and that happened to be his last flight. So I felt like, wow, coming to Michigan is pretty awesome. You just imagine something and it just happens, right? Because this is that kind of place. But what I also eventually learned is that in the laboratory, the radiation laboratory, we were just really working on things that I couldn't even imagine and I couldn't formulate with words, but that I learned and discovered because of the faculty, and in particular my advisor, Linda Katehi. So I was at the lab at the time when a lot of work was being done on space communications, and in particular terahertz technology was a big part of it. And the big thing that I kept hearing over and over is that we've got to get the weight of these flights, the launch flights size down because gas is expensive and the fuel itself is causing this to be an extremely expensive endeavor. So if we can reduce the weight, and communication systems are a big part of that, this will be tremendously beneficial to the program. So as we talk about what we do and what motivated a lot of the research in communications, reduction of size, weight, and cost is something that we just always talk about. And of course, because it's pretty high frequencies, high performance matters a lot. So for our work, that meant not only working at gigahertz, but moving to design things for terahertz. So at that time, terahertz was sort of just being introduced as a really important area for development. And in particular, we needed to get rid of loss due to radiation or dielectrics because the sources that would create the energy were very small in power. And so you wanted to alleviate that. So one of the solutions was to look at developing packages at the circuit level to reduce radiation or to eliminate the dielectric. So my project at that time was to look at integrated packaging at the circuit level. And that's the focus of my PhD thesis. So when I did that work, we did 2 things. In order to address putting what we would call a package at the circuit level, I needed to look at a different technology other than IC design, which was silicon micromachining. So it gave me an opportunity for the first time to look at a different cooking modality to actually manufacture these concepts. And these concepts basically then would allow us to look at how we were going to do that. Well, CAD tools were not as they are today. CMOS and silicon was what it has always been, lossy, but at that time, just not conceivable as a platform for RF circuits. And we expected that all of our high-speed designs would be done in some form of 3-5, not silicon. So to do this was considered pretty radical at the time, which is very commonplace now. We know how to do this. But the impact to me is that it set the foundation for my work to look at 2D and 3D packaging in silicon well beyond my PhD thesis. And it also allowed me to start thinking about what we could do with that gained knowledge of trying to make circuits for terahertz application in other domains. So as I graduate, the space program and all of that's supported about that, it goes through the ebbs and flows. And the next endeavor then is really, what would I do after I graduated from here in using the knowledge that I learned from my PhD to launch a career with microwaves. So the next part I'll talk about are two areas. One of them is communications in the more traditional sense. And then the second one is how I've used what we've been working on to launch some other areas that also include a little bit of communications and a little bit of nanomedicine. So for the communications piece, my group is called the Microwave Packaging and Circuit Technology Lab. And my goal has always been to figure out how do I bring two different things together and have them operate at really high speeds, typically 100 gigahertz, because I'm interested in being able to develop basically a highway that can support digital and analog signals. And so if you think about the digital signals having pulse shapes, you need to be able to get pretty high frequencies to keep the edges well defined. And then for traditional microwaves, we're really talking about narrowband, but narrowband that may move up into higher frequencies. So my specific objectives have always been, can I take integrated packaging and develop some type of transitions that can give me that much bandwidth? Also, can I characterize different materials, because to create these systems, it requires new materials that may be unfamiliar to this frequency range. And then we also do a lot of work with just inherent miniaturization because we have those tools available. So you may be wondering, well, what do those two pictures on the right have to do with this stuff on the left? Or you're right in the left. Well, in a way, what we've always been doing is building the nervous system for circuits. And if you think about how the human body works, we have our central nervous system that's responsible for sending signals from the brain to different parts of the body. I think a lot about that when I'm thinking about how to build circuits, particularly platforms that can accommodate different chip integrations that operate at different speeds and have different requirements. The other one is that, at least from the perspective of interconnects, it's a lot like that highway. This is a highway from New Mexico, where we're trying to figure out how do we get signals on and off. And it doesn't have to be on the same plane. They could be in 3 dimensions or on the same plane. And how do I make the signal move through the system in a way that doesn't necessarily know that it looks like that? I wanted to always think it's just traveling on a straight line. So when I first finished, the topic that came up the most was really looking at wireless communications and also optical communications. And at the time, around the mid-90s to 2000, the topic of RF photonics showed up. So RF photonics and RF photonics were really, sort of the emerging thing. It was important because the internet was just coming on board, and we needed a way to send a lot of data, which was the optical part. But wireless was also coming on board, so we needed a way to be able to interface electronic signals, particularly microwave signals, with optics, because that would be our modulation capability, and then wireless because we needed to be able to eventually pass all of this data in a wireless manner. So if you can imagine 20 years ago, nothing looked the way it looked right now. Everything was an individual component, and we were actually, most of the computing applications were personal computers. They were not laptops, and for sure not smartphones. So what that really meant is that we would need to be able to think about how do we integrate different materials together, and what do the platforms ultimately need to look like, because all of the computing was in silicon, a lot of the communications was in 3.5, and optical systems were starting to take off, particularly for optical communications, which was fiber, and then all of our wired systems were still copper. So for us, it became important to think about, when this comes together, what kind of things do we need to be able to present at in a circuit level format that would allow you to have integrated optics and integrated electronics, particularly at microwave frequencies, and look at the interfaces of those for modulation. The other thing I want to point out is that if you look at these two pictures, the one on the left sort of talks about what people were envisioning as possible. So this picture is actually, you'll see there's some routers here and there's Wi-Fi, and you'll notice that these communication systems for wireless are really tackling all types of information from different points of origin, whether it's the satellite or routers to computers or cell phones. There was just this complexity of communication capability that was required. And when you think about the infrastructure, not the devices, but the infrastructure itself, it means that you're talking about a lot of different data rates, and you're also talking about a lot of different technologies that are implemented in different formats. The other thing is on the right, that figure is really telling because it allows you to see that when we think about how things evolve from first generation down here, and I'm right around here when I finished, there's a lot of growth and development that occurred because we figured out how to put different technologies together. So most of us in this research space are either, especially if you're talking about integration and packaging, you're talking about how do you get different materials to come together so that you can build in the different circuit functions that are responsible for either the optical or the electrical functions that you want to see happen. So the one topic that I want to talk about that I'm pulling from when I first started was this design that we came up with, which is a 110 gigahertz ultra broadband vertical interconnect. And this was some work that was sponsored at the beginning of my career based on my career in the PCASE award. So if I'm trying to ultimately enhance mobile technology with these lightweight integrated systems, one of the things that I have to figure out is how do I reduce the form factor? And that required basically looking at the third dimension, which motivated a lot of the system on a package research that's been done over the last decade or so. But in particular, the transitions are a space that were not paid attention to very much because you think about things like flip chip technology or vias as a way to get signals between different layers. So what we wanted to do was to look at, is it possible to come up with transitions in 3D packaging that were somewhat seamless and transparent for your signal? So this is one project that my student worked on where if you think about a substrate where the motherboard is some kind of coplanar waveguide architecture, which is the picture at the top left, and this being your chip. If you just do basic flip chip integration, you could envision that I can get signals from one layer through to the other. But the problem is, if you look at this picture in this is a field picture, what you'll notice is that the signals are going to behave quite normally as long as the motherboard is sufficiently far from that chip. But if I start to look at how close I can bring the chip to the motherboard, it turns out that you'll start to see leakage down here, which basically gives us a lower limit on how close, when I flip this chip, I can be to this substrate. So what we found is that if it's very short, you're going to talk to the motherboard, which is undesirable. But if you create some localized separation, you could actually decouple them. So the top one is the decoupling, this is coupling. And from here, what we then recognize is that essentially what you want to do is figure out what's the minimum depth of separation between the chip that you flip and the other one versus the distance and impedances. So you can achieve that impedance matching just by looking at the minimum separation. Beyond that, no additional separation is necessary, and that's demonstrated here when you look at frequency response. Down here, you can see that this region where the signal is quite low, this is where the reflections are very minimal, and then they will start to creep up, which is basically showing that at the upper bands, this is where you're getting more talking between the chip that's up here and the motherboard that's down there. When we did that, we ultimately said, okay, so if you are content with components that operate down here, then you don't have to do much. Just making a modification in this substrate, reducing that height locally will give you as much bandwidth as you like. However, if you go to much higher frequencies, as you observe, this is starting to creep up higher and higher, say to 100 gigahertz, it only follows that trend. So then it turns out that when you look at the local point of contact, which is where the green boxes are, we ultimately have to pay attention to what's also happening here. In most of the 100 gigahertz work, most people focused on modifying the design of the chip to account for the parasitics, the L's and C's that occur at that interface. What we wanted to focus on is we wanted to give the control of the design to the motherboard designer, and made the assumption that you're buying a chip and it's already done, and you don't want to add that laborious activity to the chip side for whatever it is. So what I'm going to talk about next is just what we could do at the motherboard side and locally on the chip interface. So when you look at that, when you look at it from that perspective, I'm now looking at the regions here and here and looking at the role that they play in your response for minimizing reflections. And so what we found is that if you start thinking about just doing localized modifications using silicon micromachining, you could compensate for that here. And then we also found that you could do some compensation if you look just at the longitudinal point, because it turns out that this pad overlap plays a big role in limiting the upper frequency performance of the interface. And then the one on the right is just a picture of the samples that the student built. So if we go here and we look at these designs, it turns out that the pictures on the right show two things. They show the transmission response, which is in S parameters, which is the classical way that we observe, but they also show what happens if you're dealing with data, so that it's so we're looking at eye diagrams of that same response. So the red curve is if you had the red curve is the response of a TSV with that modification. The blue data is if I took the printed line, go up and come back down and just make one straight path, what the best limit is. So on the left, what you see is that from up to 110 gigahertz, you see this response work quite well up till about 50, and even beyond that, the transmission data tends to follow in at least a linear way the response that you would expect for a straight line. On the right-hand side, you'll see that there are three curves, and I think you can see them here, 1, 2, and 3. And again, this one being the ideal, and what it shows is that these two represent two different transition designs, and that you can actually push that out by doing better matching at the local interface. In the end, the point is that your transitions actually matter, and if you're pushing high data rates, this eye diagram can be very noisy. And what we were able to show is that when we use our transition, using the measurement data from here and doing a transform, we can get really clean eye diagrams. So you can actually enhance the performance if you know you're going to have high frequency components that are in your digital design. In your digital design. Next, I'd like to talk about what we've been doing related to healthcare. And in the healthcare sense, I'm going to give you two examples. One of them is a project related to some antennas we've been designing, specifically to look at some customized RFID systems. And then the second one will be what we've been doing to look at RFID-like nano labels for bio nano-medicine applications. So a few years ago, we had a project that asked us to think about how could you come up with a way to measure blood in refrigeration systems without taking them out manually and using a barcode, just a scanner. In the traditional sense, taking the blood out every time and handling it changes the temperature of the blood, and so that also could potentially lead to some long-term contamination concerns. But if you could come up with a labeling system that would allow you to use RFID, you could embed that in the tag, leave everything in the refrigerator, come in, and the worker would just scan and get the general temperature of each of the individual bags of blood. So with this project, we had no specifications. We just had this concept that we had to work with. And what we ended up looking at was an RFID system that had two parts. One was the IC chip, which was done by my colleague, Ramesh Harjani, worked on that portion. And we worked on coming up with an antenna design concept that we thought would be applicable to be integrated. So one of the things we were thinking about was the utilization of Fabry-Perot cavity antenna systems because they give you the capability to beam focus. And because we have a small section that we were working with, we needed to be able to get this design to be small, no more than an inch by inch in its final implementation. So in what I'm going to talk about now, it just really focuses on what we discovered by using these FPC systems, and then how we were able to, what we were trying to target for that application. So for FPC, what you basically start with is an antenna. So this slot that's shown here is placed here, and you have a lens, which is up here. And by careful design of that lens, which is a periodic structure, you can take this source, break it up into it was a 9x27 array, so N by M elements, and then they recombine to give you a more narrow beam. What we discovered when we did this is that we were able to show that it turns out that with these kind of structures, there's a near-field response that has some interesting properties. And so the figure on the left is that same configuration, but not containing everything. And the one on the right is one that's completely confined to the internals. So what we were able to see from this is that this Fabry-Perot cavity system, about 5 millimeters above, actually refocuses the beams, all of the little array of elements into this spot before you get your actual far-field response. And then for our far-field response, we also, of course, discovered that by completely enclosing this structure, we eliminate the back radiation, which is important because if this were implemented, we would not want to heat blood by having radiation go backwards into that system. So we were able to get gains that are about 13 with the ones that we designed. Now, we ultimately were trying to go for 60 gigahertz, and we ended up scaling back to about 12 because we have measurement systems for the anechoic chamber at that level. But our ultimate goal was for 60 gigahertz. In doing the near field response, we discovered something else that's been a very interesting area for us to start looking into, and that is near field beam splitting. So it turns out that with this lens, we're able to actually split the beam locally by just carefully designing that. And we've been now looking at how we can think about the near field response and what role it can play in free space interconnects, particularly for chip-to-chip communications as well, in addition to what you could get if you look at the far field. So these two illustrations sort of show this is the same lens that's been cut so that you can beam form the same one signal, splitting it into two or splitting into four. And what's been interesting about this work is that a big part of this was not only about can we make four arrays in a wireless way, but can we ensure that each one of those elements are uniform both in magnitude and phase? And we now have sort of worked out how to do that. So we are also very excited about this work because I think it's going to give us an opportunity to think about arrays and using them for vertical interconnects, particularly when you have when you want to do some chip-to-chip communications for some more complex integrated systems. Now, moving to the next topic, I have a colleague who is a material scientist, and so my department has a really strong magnetics program, and her research focuses on the development of magnetic nanowire materials. And so she and I have been working on a project for a few years now to look at can we characterize these nanowires by looking at their microwave properties, which is their ferromagnetic resonance. By looking at this ferromagnetic resonance properties, we think that you could build labels based on magnetic materials that can allow these labels to be embedded in things. And one of the things we've been looking at is using them for cancer diagnostics. So in the cancer research world, there are lots of labeling applications that you can use for biolabels, fluorescence, and the like. But in this case, we're looking at nanowires, magnetic ones in particular, and looking at how they can be used to identify individual types of biomarkers and how they can be used to increase things like throughput. So it turns out that the idea is that we know from research and collaborations with my other colleague in the vet med program that cancer cells are just inherently like these wires. And so with the proper coding, the wires go into the cells. We're trying to understand what they're doing in the cells, but we know that they go in the cells. And because they're magnetic, they have the ability to at least introduce one of the three things that you want. With most labels, you want to be able to detect them, you want to be able to separate them, and then you want to be able to identify them back. And so the cells themselves, like the wires, they take the wires up, and then they, the magnetic properties allow you to separate. So once you separate, if you use different types of wires, the question is, how do I know what I have? With some of the other labeling systems, it requires optical methods to figure that out. We think that this could be a way for us to do it in an electronic way. So the figure on the upper left is basically the ferromagnetic resonance curve for cobalt. And there are different sections. The blue curve represents one orientation and the orange curve represents the other. And then this is the conventional measurement that we will take that will eventually produce that data. So from what we've been doing so far, we've been able to come up with the curves for both cobalt, iron, and nickel. We are able to detect fairly low levels of that. We're looking at array chips of those wires, and we are exposing those wires to pretty high fields. We're at a Tesla to a Tesla and a half to see where some of the resonances are. So these materials are, as wires, tend to start to show resonance properties above 18 gigahertz. So this is really a microwave problem. And we're pretty excited about it because in the spirit of being able to make a label, what you really want to be able to do is to say, if I put two different types of wires in a biological system with the proper coding, that I can detect those two different frequencies. So the picture on the right just says the top curve being if I were to stack these wires, the blue curve being if I were to put them next to each other. At least in chip form, we are actually able to detect where we see nulls, which represent the corresponding proper B field, which is an external DC magnetic field at 28 gigahertz. And so we're pretty excited about this because now, for the first time, we are able to start playing around with how you could actually make them as barcodes. And then the last thing is, of course, I'm a microwave engineer, so I always want to see how useful and good would this be in a traditional microwave application. This is an application, now that we know what the properties look like, we can now characterize the wires, and then we just did a preliminary study on a circulator. So this design is a circulator. It's a disc here, it's a round disc, but in its implementation, we did a paper at RWS last year. We used a triangular one because that was easier to cut. But basically, we have nanowires that are mounted on top of this CPW structure. And the wires themselves are made in a host that's aluminum oxide. So it's a porous host, and those pores are used to actually, you fill those pores with the magnetic material. And so on the right, we have this data that basically says that when we think about the isolation, the red and the blue, we are able to get about 12 dB isolation. We know from simulations that if we grow these a little bit thicker, which is what we'd like to do next, that we can get isolations as high as 31 dB, which I think is very impressive for nanostructures, and it's also pretty good, particularly for this frequency range. So it's another area that we're currently exploring. So that is at least a little bit of an appetizer, a bite of what I've been doing over the last few years. But my big takeaway, and the thing I would want students to know, is that what you learn now is the foundation to what you'll do later. But everything we've worked on really informs and guides us to this direction. That the magnetic work in particular, my colleague and I have been in Minnesota for probably most of my career there, but the work was not mature enough for us to do this work until more recently, in the last few years. So we're pretty excited, but it was a 10-year journey for both of our work to get to a point where we could cross over. So for me, I'm working still a lot with communications. I love that topic, particularly and also love doing anything that has to do with integration. We've done work with bacterial thin films. We have people who want to know how does bacteria conduct electronically? So that's a materials problem for us. We've helped with that. And I really like the development of diagnostics, which is a good part of what I'm going to be working on moving forward. I'd like to shift gears and take the remainder of the time to just talk a little bit about faculty and what it looks like for women and for minorities. So we've talked a lot about this, so at least through my career, about how important it is to diversify the faculty and about gender balancing. So, it took about 50 years or so for it to kind of look like that. It's not quite like that, but it's kind of hard to put a fourth of a person or half of a person if you look at things on average. But I think a lot of programs really are at about 20%, not all, but that's an important goal, and it has taken a long time, this much time to get there. If we look at it by both gender and race, it's going to take some time, but the reality is it will eventually have to have some combination of both. And with that level of complexity, it just means we're all going to learn a lot about each other, but I'm confident that we will get where we're trying to go, even if we're not getting there at the speed that we would like. So I want to tell you a little bit about this topic. I was asked to talk earlier this year to a group of women who wanted to understand why are there so few African American women who are full professors. And I was like, really? Okay. Well, I've done some discussions about women, and I was okay with that. But I also knew when I was going to that talk that I was really worried that, was I going to be that presenter that gave bad news and made them feel as bad as I felt when people were showing this stuff to me when I was a junior faculty? And I thought, I know that's supposed to be helpful, but it's really not very helpful right now. So I had to do a lot of soul searching and praying on that flight of, please give me something that will empower them, because I don't have good news, but I do think any good engineer wants to know what the reference point is, because you can't improve something if you don't know where we're starting. So what I'm gonna talk to you about next is really about establishing reference points, and also about what I think we need to think about in terms of history. So turns out that civil rights and the pathway to full professor go kind of hand in hand for women as well as for minorities. So I think one of the things we don't think a lot about, and we should be reminding ourselves, is this evolution. So I have 3 layers here. The first one is just, the left side is talking about civil rights and just what happens here in America, and then the right hand side talks about how you make an engineer. So one of the things I wanted the ladies to take away from was that, look, civil rights started in 1964. I know we all live in a time where there are all these advances. We're used to living in nice hotels, and we've got smartphones, and you just think it was always this way. But 1964 was not that long ago. That was 54 years ago. Well, guess what? It takes 22 years to grow an engineer. That's assuming you made all of the right choices along the way. So I use myself as the guinea pig, but basically that means that from 64, if a person were absolutely prepared to become an engineer, by 1986 they could have been one. And I showed up in 88 as an undergrad with a BS degree. And then if you look at civil rights 32 years later, if we think about generations, a generation is about 30 years. So the first generation, which is this window of time, it takes another 2 years to get a master's. So I'm 1990, 1988 would have been about right. And then it takes another 3 to 5, if you're lucky, to get a PhD. So that would have been 93. Okay, I'm at 94. So our first surges of Prepare Future Faculty programs started in the mid-1990s. Before that, no one was talking about how to become a professor. It was just assumed that you knew how to do it, I guess through osmosis. But no one was discussing it. Those programs started in the 90s. And I remember because I was here and they were asking me, hey, would you like to help start one? And I was like, I got to graduate. I just got to focus on graduating because I don't know how to graduate. I just need to graduate. But I'm really glad that they started those programs because a lot of the younger women faculty students participated in those programs. And I think that that really helped them at least to kind of process out what was going on. But then if you look at the next 25 years, now we're talking about the first and the second generation. So that really means that's going to put me to 2024. We're not that far from that. I go and decide, yes, I'm going to become a professor. I have no idea what that really means because I did not participate in Future Faculty program, right, which was just starting. But to become an assistant professor, that's 6 years. So now I'm at 2024. And then to become an associate, that takes another, most people do it in 6 to 12 years, so I'm somewhere in the middle there. I'm at 2013. And the advanced programs at the National Science Foundation started in 2001. So somewhere between here, not at the beginning of my career, but somewhere between here, they say, oh, we need something to help talk about this topic for women. Well, I'm in the trenches, right? And I got to make the best of whatever I know. I mean, am I playing spades? Am I playing gin? What game are we playing? I have no idea. I just know I have to play. And then the second phase of NSF programs start here. So I guess my point is that even if everything went according to plan, if someone started in 1964 that looked like me and did everything right, at best they would be full in 2011. And I was 2013, plus or minus, some, ups and downs. So part of it is that we need to understand this is a long process for anybody. What I just presented is not just my story, it's every professor's story. Some people do it faster, but if you do the average, most people will follow this trajectory. So when we're thinking about faculty and whether or not we give due diligence to our women faculty or minority faculty, I think all of us need to understand that when an opportunity presents itself and we let it go by, that's 1 year, one of many years that's going to take to grow that professor who might be able to become a full professor. And when I thought about it that way, I was like, wow, it's a good thing I didn't know this before I started. I don't know if I would have done it, But it made me feel a lot less overwhelmed and stressed out about the journey I've taken, because it's been a challenging journey. It's been a good journey, lots of things that I never imagined, but it's a lot harder than I thought it would be. And I really wanted those ladies to know what you're doing is so important. And all important work is hard work. Unimportant work is not hard. Important work is really hard. But I also want faculty to know that what you do matters, because I'm only still here because there were select professors who helped me along the way, who just, were able to just push just a little bit. No one's asking you to make this a full-time job, but when I passed by them, they gave me that little extra nudge. Whether I was struggling or doing well, they just believed in me. And when I think back and I think about students now, I really think about how we think it's about, I don't want to tell someone what to do as if I'm going to give them an advantage, but most of the students we're dealing with are really smart and capable. I really think what people need is encouragement. And I will tell you that for every time, and I've had I can say this now, I've had a love-hate relationship with this. I mean, I've been about to divorce this job many times. But what has kept me here is that just when I'm about to say I'm done, I'll see one of my professors who says, how's it going? And I don't know, something happens, like some kind of, metamorphic transformation. And I just feel like, you know what, I could try this one more day. Today was just a bad day. So I just would like for you guys to know that, as students, what you're doing is really important. It takes a long time for anybody to become an engineer, and it takes a really long time for anybody to get a PhD. And if you decide to go the faculty route, it takes a really long time to become full, because it's hard. But it's important, because without us, a lot of the things that I kind of tried to talk about with NASA and all of these big problems that people are trying to solve, they can't be solved without the depth of knowledge that we learn and develop through the various projects that we work on. And that's not trivial. So this is how I started that. So let me tell you a little bit about data. So the point is that the pathway to steady state, in my opinion, is that it's going to take a few generations. And the way we're going to get there is by everybody doing what they can, giving due diligence, a little bit at a time, a classmate being open to talking to someone who's a little bit different, and maybe trying to understand why we're not communicating properly. A professor seeing a student and looking at whether or not they're giving due diligence and giving them a little bit of guidance, because maybe that person doesn't have anybody else to talk to. Unfortunately, my professors, whether they knew it or not, they were it for me. I couldn't necessarily always depend on my peers, but my engineers were my professors. And I spent a lot of time in some of their office hours, and they all got to know me very well. But they were my lifeline to that pathway that got me here. And if they had all shut down and not allowed me to talk to them to learn, there would be no way you could do this by yourself, because it's not that type of path. So I think this is what's going to be necessary. There are going to be a lot of things that can come and go. And I think the takeaway for the young ladies that I was talking about is to say, look, you guys are thinking we're at steady state and you're disappointed. We're not. You are a pioneer or a leader, because we're still, in that part of my life, I was up there and I didn't know it. You're still pioneering and leading, and you're innovating. And this is where you are. Eventually you'll get here, and eventually you'll be a disruptor, and you'll have the opportunity to decide, I'm going to settle. But until we get to here, right, you got to keep recognizing where we are, and then try to make sure you get as many resources and tools that are available to you to support you. Go to those programs, find professors that will talk to you. Sometimes I'd have to hit quite a few to find one that was open, but they're always there, believe it or not. And I really appreciate that, because it has made a big difference for me. So the state of affairs are the following. The Big Ten plays a big role in women faculty. In terms of just tenuring of faculty, this is everybody. If you look at the Big Ten, Michigan is at the top. You got a lot of faculty here in engineering. So this is engineering as a collective. And so what Michigan does matters. If Michigan doesn't have women, graduate students or undergraduate students or faculty, you got a lot of slots. Imagine them having a lot more than you, right? That's going to be hard to do. So the boxes that I've put in are the Big Ten of all of the institutions. And I think of course, I didn't know this when I was coming through, but Michigan has fared quite well in terms of having positions. And then when you look at where women faculty are, the slide on the right just kind of shows who has the most tenure track faculty at that time. So if you look here, this is by percentage, right? And then if you look over there, that's the whole school. And then one of the things I thought was interesting is I was kind of curious to say, well, like in all of the different disciplines, where do we show up? And of course, I'm particularly interested in this group, but most faculty are in this portion, not in this portion. So that's the other thing to keep in mind, is that whether you want to or not, these disciplines have to own it, because that's where most of the people are going, and that's where you're going to get. That's where most of the students are going, which means that's where most of the faculty can come from. And that's about 91% of the possible options. And then if you go to my cohort, then you start to notice something very interesting. It turns out that the groups that are larger, which I put stars by, right, are here. And look how small, these are numbers now, this is not percent. This is how many people are in there, at least as of 2014. This is how many women, African-American women faculty. So of course now I want to know, because I'm an electrical engineer, and that I'm somewhere in this number. That's tiny, right? 8 people. So if you look at research, most researchers are working with each other. And so it matters if we're connecting. If you're relying on people to connect with their cohort, if you don't have a cohort, then it means I have to connect with you. And it's important that you keep that in mind. And then the last thing I just want to say, I think I'm almost to the end here, is that our growth rate was about 1.27 a year. That's kind of small. So I think to me, I hope that once you know that, it'll just motivate you to say, look, I need to give a little bit more effort. If everybody did twice as much effort as what they already do, I think this number would increase. And for electrical engineers, we're up there. You'll see that the numbers between 2011 and 2012 have increased. They were 12, and now they're about 26. So it is increasing, it's just that it's increasing at a really slow rate. And then finally, this is the rankings. So, and this is everybody for all disciplines. And so this is what had the ladies concerned. They were like, oh my God, I'm like in this, and then I'm never gonna become full, right? And that's kind of scary because you're like, that's a lot of work to get to the very last stage and just say, it's not gonna happen for me. And I really wanted to encourage them to say, yes, it's gonna happen to you, but this number reflects that journey from civil rights to that point. In more time, these people are gonna go here. And the proper balance, which for most groups is small assistant, next largest is associate, and then the largest is full, it will flip.